Hi, everyone. Welcome to week 3 plus 10. Welcome to week 13, sorry, of Com 386 and learning about statistical analysis. So we're going to go ahead and get started. I promise I know what week it is. So statistical analysis. This week, we're going to talk about what that is, why we're using statistical analysis, defining it, 3 common statistical analyses, and then we're going to look at illustrations that use class data y'all are familiar with to kind of show you what statistical analysis is and what the differences between these 3 common ones are. And just to kind of give you a heads up, the 3 common ones that we're going to talk about are chi-square tests, t-tests, and correlation. So keep those in mind. And as you do, keep this question in mind as well. Why statistical analysis? So, statistical analysis is useful in quantitative communication for 3 primary reasons. So, we know what bivariate crosstab tables are. We've done them in this class. We know what it looks like to look at them and look at the percentages that they show us that might look like they show a relationship between variables, but we don't know how different those actual percentages, how different those percentages actually are. So, we need a way to know that the relationship in the sample is also probably there in the population, which is why we use statistical analysis. So statistical analysis helps us make sense of data by summarizing information, which is descriptive statistics, and by allowing us to infer population characteristics from sample data, inferential statistics. So you may not be familiar with what those 2 terms are. Descriptive statistics are actually what y'all have been doing this whole semester. And so that's kind of looking at things like the mean, median, mode, range, standard deviation. Whereas inferential statistics are going to tell us if what we're seeing in a sample would be present in the population, which is what we saw on the slide prior. And that's going to be the focus for this week. So a couple of important terms to kind of note. The first being alternate hypothesis. So that's simply our hypothesis, and it's what we predict to observe in our data based on some theory or fuller understanding of the world. And you may not be familiar with alternate hypothesis as a term, but that's actually what you've been doing every homework that you've turned in, is proposing an alternate hypothesis. So you've been proposing some sort of relationship between variables, and that's your alternate hypothesis. And it's denoted with a capital H and then this capital A, but lower than the H. So then we also have the null hypothesis, and that is the unstated presumption that our 2 concepts aren't related. And a lot of the times you don't say the null hypothesis, it's based off, it's the opposite of your alternate hypothesis. And null hypothesis is going to be denoted by this capital H and then a 0 below it. So when we have statistically significant results, what we say is that we reject the null hypothesis in favor of the alternate hypothesis. When we don't have statistically significant results, we fail to reject the null hypothesis because there's no evidence of a relationship. So note here in bold, rejecting the null hypothesis, failing to reject the null hypothesis. When you're kind of describing whether or not you've got statistically significant results, you want to center what you're saying around the null hypothesis, saying we reject it or we fail to reject it. It's never that we accept the alternate hypothesis or that we reject the alternate hypothesis. We either reject the null or we fail to reject the null. So we've got some important statistical ideas to run through as well, and the first being a test statistic, the second being a comparison value, and the third being a p-value. So we're going to talk about what those are now. So a test statistic. Every statistical test has an associated test statistic, and remember, our statistical tests are the 3 we mentioned earlier in the presentation. And for the three tests we're learning in class, these are the tests and the test statistics associated with them. So we've got our first chi-square test, and to accompany it is the chi-square test statistic. Second, we've got our t-test. T-statistic accompanies that. And then third, we've got correlation, and correlation coefficient is its test statistic. And something to note with correlation coefficient that you may have inadvertently known is that it's denoted by a lowercase r. So whenever you see that, that's your correlation coefficient. So next idea is a comparison value. So in addition to the test statistic, two of our tests have a comparison value that indicates the significance of the test. So the comparison value is going to be a target value or threshold for achieving significance. So first, when we've got a two-way crosstab table, which is what we use with chi-square tests, our comparison value is going to be 3.84. When we have a t-test, our comparison value is 1.96. And then for correlation, we don't use a comparison value. So what this means is that we've got a statistical test and it's going to be significant if it is greater than or equal to the comparison value. So if you are looking at your chi-square test statistic and it is lower than 3.84, it's not going to be significant. Same with your t-stat. If it's lower for your t-test, your t-statistic, if it's lower than 1.96, it's not going to be significant. But if either of those are greater than or equal to 3.84 and 1.96 respectively, then it will be significant. So keep in mind that these target values, these comparison values, with the comparison values specifically, you need to reach that number at a minimum or be higher than that to have significant results. With your p-value, so this is the last concept we're going to talk about, it represents the level of significance for a statistical test. And a statistical software program will always give you a p-value with any test. And so the standard p-value is 0.05. And so this number means that when you're collecting data, if you collect it from a population 100 times, you'd expect the same results 95 out of 100 times. In turn, you'd expect to reject the null hypothesis 95 out of 100 times. And so a p-value less than 0.05 means you have a significant result, but if it's higher than 0.05, you don't have a significant result. So just kind of keep in mind your comparison values, they have those thresholds that need to be at or above that number in order to be significant. With your p-value, if it's at 0.05 or below, you would have significant results. So just kind of keep in mind that difference. So some common statistical analyses, which we've talked about, we are also going to kind of just look at and give you all a better idea of how those look and what to do with results that you would get when testing for these, like in testing for significance of relationships. So first is your chi-square test. So a chi-square test is a statistical test for association between two categorical variables. And it tells us the probability that the sample at hand comes from a population where there is no association between the two variables. So you may or may not have a relationship between your variables, which is why you need to see whether or not you do. So we have this example hypothesis. Among NC State students, women are more likely than men to select pink or purple hair as their favorite, or pink or purple as their favorite color. This whole time I've been looking at this, I don't know why I default to hair color, but just favorite color. They'd be more likely to select pink or purple as their favorite color than men. So that is your alternate hypothesis. And you want to test to see if this is true or not. So we've got our results here, and we're not going to actually go into too much depth with this just yet. Sorry, I am tongue-tied at the moment, but we're gonna just to kind of like show y'all what that looks like. We'll be coming back to it later. But essentially, if you've got this hypothesis and you see that your results are significant, you would reject the null hypothesis because it seems probable that women are more likely than men to choose pink or purple. So just kind of note that. And again, note the wording of how you reject or fail to reject the null hypothesis. So t-tests. T-tests are a statistical test for differences between one categorical independent variable and one continuous dependent variable. So it tells us when two groups represented by our independent variable categories are different enough from each other to support a hypothesis. Okay, so we've got a new hypothesis we're working with here. So among NC State students, women cook more often at home compared to men. We've got a couple of just kind of assumptive hypotheses, but that's okay. We're going to work with them and we're going to see what our data tells us. So this is what, and if we were using SPSS and doing this in person, this is what your output would look like. So just kind of note that. And here are some important stats to just kind of note. So you've got your, you've got your independent variable here, sex, female identifying, male identifying, and then you've got your independent variable being cooking at home. And so if you look to see, we have 88 people who are female identifying as our sample here, and 46 are male identifying. And then we see that we've got differences in means, differences in our standard deviation. And also just to kind of note, the cooking at home variable is how many meals per week were cooked at home by both of these things. So just kind of note that. And also note here that we will get results and we'll talk about the results, but we have a pretty low population because it's 134 people. So it's not very many people. We also have, like small sample size. It's convenient sample just based on how this data was collected, and we've got a pretty big difference in terms of how many female identifying people there are and male identifying people. So just kind of like note that, but we will still talk about the results. So what we have here is the mean difference. So the mean difference is just taking this number and subtracting this number, and then you get your mean difference. So very simple. You've got your t-statistic here, which again, note that threshold of 1.96 as the t-statistic that we would need. And then here we have got our p-value, and that is 0.148. So that is way higher than 0.05. So t-statistic is too low. P-value, which is denoted by sig here, is too high. And because of that, we would fail to reject the null hypothesis because there doesn't seem to be evidence that men and women differ in their frequency of cooking. Okay, so correlation. So correlation is a statistical test for association of two continuous variables. And it tells us when two quantitative aspects of our sample are associated enough to correspond to a trend line that's either going to be positive or negative, or not associated to, which is going to be a flat line. And we're going to look at what these trend lines and a flat line look like. So we've got a new hypothesis. Among NC State students, there is a relationship between age and amount of time spent using social media. So what that might mean, and maybe something to consider here, is that the older you get, the more time you spend using social media. And we want to see whether or not that's true. So we've first got a positive correlation between age and social media use. So that would note that the older you get, the more you're using social media. And that would mean that you have an R value, your correlation coefficient is going to be greater than 0.00. So it can be between like up until 1. So anything that's above 0 up until the number 1. If you've got a negative correlation, you can see the older you get, the less likely or the less time you spend on social media, which probably is more accurate, but you have a lot of older people who use Facebook a lot, so who actually knows? And if you've got negative correlation, you will see that R is less than 0.00. So whereas with a positive correlation, it can go up, it has to be higher than 0, but can go up to 1. With a negative correlation, it's got to be lower than 0, but it can go to -1. And if you have no correlation, you've just got this flat line, no relationship. Everybody's using social media for the same, it says cooking at home there, but hours on social media, same amount of time, no matter the age, then R is always just going to be 0, flat out. So just kind of note that. And so here we've got this really cool symmetrical table. So you've got age, which is your independent variable, and then you've got social media time, which is dependent. And as you'll see here, age, and then you've got them up here as well. So age correlating with age is 1, social media time correlating with social media time is 1. But then you can see the actual amounts here. So when you look at age related to social media time on both ends, that gives you the actual, that gives you the actual amounts. R, your correlation coefficient, and then your p-value or your significance. And so again, to just kind of note what that would mean. So if you've got this negative number, that means you have a negative correlation or relationship, and we'll go back to what that means. So it would look like this. So as we increase in age, we decrease in the amount of social media use. And then here, your p-value would need to be lower than 0.05 to be significant, and it's very high. So something to kind of note with your Pearson's correlation, so R, that correlation coefficient, is that something that would be significant would be much higher than 0.7 or 0.074 or negative 0.074. So if we had a negative 0.3, negative 0.5, that's going to be much more of what we're looking for in terms of defining significance when it comes to measuring the correlation coefficient. And again, we would need a p-value less than 0.05 to be significant, which we do not have. So based on that, we fail to reject the null hypothesis because there isn't evidence of a correlation between age and social media time. Okay, so we are back on our cross-tabulation table to talk a little bit more about our chi-square test example. And again, going back to the male identifying, female identifying students and their preferences for pink or purple or another color. So again, we might assume that women would be more likely to pick pink or purple than men would be. And we can see here with these percentages that if you just look at the percentages, maybe you would think that's true. So you've got 4.2% of the male identifying respondents picking pink or purple as their favorite color, and half of your female identifying respondents picking pink or purple. Oops. And so if you go down here to your chi-square test statistic, you've got your your Pearson chi-square value. You again would need it to be higher than 3.84, and it is much higher than 3.84. So that's kind of something to note. You would also need a p-value to be lower than 0.05, and that's what you have down here as well. So you've got a much higher chi-square test statistic, and then like a lower p-value. So you can, which is what we just did, you can look at that amount and see if it's greater than 3.84. And if it is, you can say your result is significant. You reject the null, and you don't reject the null. If it's not significant, you can also look at the p-value. And if it's less than 0.05, then it's significant and you reject the null. If it's not, you fail to reject the null. So just to kind of look at that again, in this case, we would reject the null because we have significance on both ends with our chi-square test statistic and with our p-value. All right, so we made it through this first video. So what we did was introduce some important statistical terminology, which again, probably important to just make note of what that is, take pictures, whatever is best for you to keep up with this. We also became acquainted with our 3 common statistics tests, our chi-square tests, t-tests, and correlation. And then we learned the basic ideas for interpreting statistics tests. And we have a couple more videos this week. The next being doing and interpreting statistics, and there will be a workshop on Moodle for y'all to work on that kind of relates to that. And then we're going to do a chi-square tutorial, and you kind of got a taste of what that looks like in this module, but you'll get a better idea in that 3rd video. So thanks for sticking with me through this first video, and I will see y'all in the next one.